Students, hi, this is Mr. Bob. In this video, I'm going to walk through how to solve a sample series circuit problem. This problem comes from physicsclassroom.com, the concept builder that's located there. And I urge you to go to that concept builder to get more practice with this if you feel like you need to after watching this video. So notice there's this big table here, and there's this circuit that we have. The circuit has a battery, has two resistors, and it's a series circuit because there is just one loop. There's no way for the current to go in any other path other than the one path shown here by the circuit. I'm not going to do all the 6 examples. I'm just going to do sample A and example F. Two important concepts to keep in mind throughout this video are listed down here in purple. And the first one is that any circuit elements that are in series with each other experience the same current. The second important concept to remember is that for resistors in series, to determine the equivalent resistance, basically what you need to do is you need to sum up the individual resistances of each of the individual resistors. So R equivalent equals R1 plus R2 plus R3, et cetera, et cetera. So with that in mind, let's tackle this problem. So first of all, example A. So basically, example A tells us our givens are that the battery voltage, all right, is 24.0 volts, and we're given that R1 equals 4.0 ohms, and we're given that R2 equals 8.0 ohms. And we're asked to figure out the equivalent resistance, the current at point A, the current at point C, and the potential potential at point B. I'll talk about that here in a second. First of all, let's just walk through this. So to figure out the equivalent resistance, we're just going to apply our equation that we just talked about. So we're just going to sum up 4 ohms plus 8 ohms. And that would give us an equivalent resistance of 12.0 ohms. So we can fill that in here. Actually, I need to fill in there we go. Cool. Now, how do we figure out the current? Well, remember that Ohm's law says that the current going through any resistor element is equal to the potential difference across that element divided by the resistance of that element. But also, Ohm's law can be applied to an entire circuit, and that's what we're going to do here, because if we want to figure out the total current flowing through the circuit, then that would be, in this case, the potential difference across the battery divided by the equivalent resistance. And so since we have the battery voltage as 24 volts, or the potential difference is 24.0 volts, and we know the equivalent resistance is 12.0 ohms, and we do that, we figure out that the total current flowing out of the battery is 2.0 amps, okay? Now, in this case, because this is a series circuit, if I've got 2.0 amps here, I'm also going to have 2.0 amps here, and here, and here. Because remember, in a series circuit, there's no other place, there's no multiple paths for the current to go. So the current is continuous, or it's the same value throughout a simple series circuit like this. And again, we're just invoking rule number 1 if you want to think of it that way. Any circuit elements that are in series with each other experience the same current. Okay, so that means that this is 2.0 amps and this is 2.0 amps. And I keep forgetting that I don't need to list the units. There we go. All right, now the last question, the potential at B, okay? I just want to emphasize again that when we talk about electric potential voltage, I really like to think of it, and I want to urge you to think of it as actually potential difference, delta V, because it's the potential difference across circuit elements that really is conceptually, I think, is the strongest way to think about it. Now, we have an assumption that we make often in circuits, and they've certainly made it in this problem, that on the negative side of the battery terminal, if we call this this is kind of like the ground level, so to speak, we're going to say the potential at C, VC equals 0. So in other words, if you want to think about it, we're establishing our reference level for potential energy. If you remember that from gravitational potential energy, we have to set some reference level to be 0. Oftentimes it's the surface of the earth or the ground. In this case, for electrical circuits, a lot of times it's the spot near the negative terminal of the battery. So in other words, the potential at C is 0. We also know that if the battery voltage is 24 volts, that the potential at A, VA, is going to be 24 volts, okay, because it's going to rise when the electrons basically travel through the battery. They gain 24 volts of electric potential. So the question is, what is the potential drop across resistor 1? Because if we know it's 24 volts here at A, all we need to figure out is what is the delta V1, right? How much it drops, then we can take 24 volts and subtract how much it drops from it to figure out what VB is. So I guess what I'm going to say here is that potential at B equals the potential at A minus delta V1. And I really don't like the way this is working out, but I'm kind of mixing terminology here. Just remember again that potential difference is really the way you want to think about this. So what is delta V1? Well, delta V1, if I just use Ohm's law, remember Ohm's law can be used on individual circuit elements. So I1 equals delta V1 over R1. In other words, the current going through resistor 1 is going to equal the potential difference across resistor 1 divided by the resistance of resistor 1. So if I solve that for delta V1, then I get 2 amps is the current. We already know that. The resistance of resistor 1 is given to us as 4 ohms. Whoops. I don't know what happened there. Four ohms. So we get 8 volts. Okay. So that means to figure out our potential at B, all we would do is say it's 24 volts minus the 8 volt drop. So the potential at B is 16 volts. Some of you might be thinking, couldn't I have just figured out the potential drop across resistor 2? And that would have given me the answer? Yes. All right. If you want to think about it this way, you could start here in the lower right corner and work your way backwards to B. And basically all you're doing is the potential is rising by a certain amount because you're going in the opposite direction that the current is actually flowing. And this kind of gets to Kirchhoff's law, which those of you in HL physics were studying. Okay, so so I just did that. So this is 16. So there we go. We've done part A, or example A. Let's go down now to example F, and maybe I'll choose a different color. Yes, let's do that. And we'll do it right here on the side. So hopefully we don't have to keep scrolling up and down. And let me also then erase some of this stuff here because I might mark it again. Okay. So in part F, we have new givens. We have a battery voltage of 48 volts. We have resistor 1 being 6 ohms. So let's just do that. Battery voltage equals 48 volts. R1 equals 6 ohms. And we are told that the potential at B is 36 volts. Okay. So we need to figure out a couple different things here. So this is what I love about this problem is we have to work backwards actually from the way we solved the first problem. Because the first problem we're given a lot of information to help us figure out the current coming out of the battery. In this case, we're given more information about potential along the way, and we're given information about the battery voltage. Okay, so so if the potential drop across B, or excuse me, if potential at B is 36 volts and the potential at C, remember we said this is true about this problem as well, the potential at C is 0 volts, then what is the potential difference across resistor 2? Well, it's just going to be 36 volts, right? Because it has to drop that 36 volts from B to C. Now, we also know that the battery voltage has to equal the potential drop across resistor 1 plus the potential drop across resistor 2, right? That has to be the case. So we can actually get the potential drop across resistor 1 by basically taking the battery voltage and subtracting the potential drop across resistor 2. So what we're saying here is 48 volts minus 36 volts tells us the potential drop is 12 volts across resistor 1. Awesome. So now we have information that we can use, because notice we know resistor 1 is 6 ohms. So now we can use the idea of Ohm's law on resistor 1 to figure out the current going through resistor 1. So I1 equals delta V1 over R1, or I1 equals 12 volts over resistor 1 is 6 ohms. So we get that I1 equals 2 amps. Awesome. We have 2 amps, and that is a huge thing in a series circuit, a huge thing to figure out the current in a series circuit, because we know that's going to be the case in all the spots. So we can now fill in that this is 2.0 amps. We can also fill in that this is 2.0 amps. Okay. And so then from there, what can we say? We have to figure out the equivalent resistance and resistor 2. It doesn't matter which way we go about this. Actually, it does. We have to figure out resistor 2 first. So for resistor 2, we're going to use Ohm's law applied to it. So delta V2, excuse me, let's start this way. I always like to start this way. I2 equals delta V2 over R2. The current is always the potential difference divided by the resistance. We're solving for R2. So the resistance is going to equal the potential difference divided by the current. The potential difference across 2 we already know to be 36 volts. And the current we already deemed is the same throughout that circuit, so it's 2 amps. So that gives us an R2 value of 18 ohms. I can fill that in right there. Okay, and so finally, the last part of this, fairly straightforward to figure out the equivalent resistance. Let me just go down here. I'll go over here. The equivalent resistance is going to equal R1 plus R2. So we know that R1 is 6, R2 is 18. So the equivalent resistance is 24 ohms. We can fill that in here. Okay, so I hope that was helpful. And again, please feel free to reach out to me, or please seek more practice on physicsclassroom.com. Thank you.